So a super quick review of everything, really of the last like 3 lessons is kind of here, isn't it? If I have a function where the first derivative is equal to 0, that gives me critical values, right? Those are possible values of local maxes and mins, okay? The second derivative equals 0 is where we have PPIs, potential, I'm sorry, not PPIs, PIPs, potential inflection points, right? Now, again, I said these are possible extrema. These are possible inflection points because we don't know if that happens unless we look at increasing versus decreasing, right? So if I change from positive to negative second derivatives, then I had a max or a min. If I went from concave up to concave down, then I had a point of inflection, okay? And that's sort of everything that we sort of did in one quick little section here. All right, so here's what we're going to do. And this is, we kind of got into this a little bit towards the end of our last lesson. I'm going to give you facts. And from those facts, what I want you to do is create a graph of the original function. Sound good? All right. So here's our facts. Ready? Fact number 1. First derivative is greater than 0. Translate that into English words. First derivative is greater than 0. Slope is positive. My graph is increasing. F of x is increasing from negative infinity to 1, right? So that's our first fact. Second fact, f prime of x is less than 0 on that interval. Translate in English. F of x is decreasing. From 1 to infinity. Is there anything that I can say based on these 2 facts? One is a maximum. Now, why is 1 a maximum? Because at 1, I changed from increasing to decreasing, right? My first derivative changed from positive to negative, right? So since I was increasing and then decreasing, 1 had to have been a maximum, okay? So because of these 2 facts, I'm actually going to say x equals 1 is a maximum. All right, so that's what we got from part 1. Part 2. Here's what we know is true. Second derivative greater than 0 on that combination of intervals. What does that mean? Graph is concave up. F of x is CC up. From there to there. And then we have this fact. Second derivative is less than 0 on that interval. That means my graph is CC down. Anything that those 2 facts tell me? Well, I'm concave up from negative infinity to negative 2, concave down from negative 2 to 2. So I went from concave up to concave down at what point? Negative 2. So what does that make negative 2? An inflection point. All right, then I went from what? So I was concave down from negative 2 to 2, but then from 2 to infinity, I was concave up. Another change of concavity, right? And that happened at X equals positive 2. So I'm going to just do this. X equals positive and negative 2 are inflection points. That cool? These last two facts brings us back to something from our first unit. What does this say? This is the limit as x goes to negative infinity of my original graph is negative 2. What does that mean? When I give you a limit at an extreme, what is that really telling me? As I move to the left, my graph approaches negative 2, right? It's a horizontal asymptote. That's exactly right, right? So I'm going to have a horizontal asymptote at negative 2. But again, where is that horizontal asymptote occurring? As I move towards negative infinity, right? So as I move to the left, I'm approaching an asymptote at negative 2, okay? So I'm going to put that in English. Ready? That means f of x approaches negative 2 as the graph moves towards negative infinity. Actually, I'm going to say x equals negative infinity, which is really kind of like terrible, terrible math writing, right? But you get the idea, as x approaches, right? Okay, and then what happens here? As I move to the right, the graph approaches 0, right? So as f of x approaches 0, as the graph moves towards positive infinity. All right, take all these facts and let's make a graph. Boom. Boom. So here's what we know. All right, so here's what we know. I am increasing from negative infinity to 1, from 1 to infinity, and 1 is a maximum. All right, so at 1, we're going to have a maximum. I'm going to put a point right here. There it is. There's a maximum. Local maximum, right? Then I have some concavity. We'll talk about that. I have inflection points at positive and negative 2. We'll talk about that. How about these asymptotes? Those are kind of important, right? Okay, so I know I'm going to have something happening at negative 2. I know I'm going to have something happening at positive 2. And then I have these asymptotes here. And here. Those are the two things I have to approach, right? So what is this saying? As I go to the left, I got to approach this, right? As I go to the right, I got to approach this, okay? Now I just got to put some lines on here and see if we can make it look like what's being described. So my graph needs to increase from negative infinity to 1. Hey guys, from negative infinity to 1, my graph has to increase. So I have to approach this asymptote from the top, right? Okay. So I know it's going to wind up doing this. Is my graph increasing as I write that? Looks good, right? And I have to keep increasing until I get to what? Until I get to 1. And then I have to do what? Then I have to decrease from 1 to infinity. Okay. It says that my graph needs to be concave up from negative infinity to negative 2. Is my graph concave up right now? Is it facing upwards? Yeah. Then from negative 2 to 2, so between here and here, my graph needs to be what? Concave down. So watch how I'm going to draw it. I'll put a point here. I'm going to change my inflection here. Do you agree? Concave up, concave down. Cool, right? I'm gonna keep being concave down until I get to 2, and then I'm gonna change to being what again? Concave up. Concave down to concave up. And there's your graph. So there's an inflection point. There's my inflection point, right? So look between these points, B. All of that's concave down, right? All of that's concave up. All of that's concave up. I'm increasing from negative infinity to 1. I'm decreasing from 1 to infinity. I'm approaching this asymptote. I'm approaching that asymptote. All looks good, right? Okay. So again, it's a process of getting the facts, creating your graph. Cool? I love it. All right, guys. Here's what we're going to do now in example 2. Okay. This is some graph. Okay. What it says in part A, it says, if the graph above is f of x on a closed interval, then answer these questions about f of x. Well, what did I say at the beginning? I said, if the graph above is f of x. So talk to me. What's happening for decreasing and concave down? Is this graph decreasing and concave down anywhere? All right, so where is it decreasing? Well, decreasing would be what? Where it moves from a higher position to a lower position. So would you agree that part's decreasing? Would you agree that part is decreasing? That cool? Any other part decreasing? Good. All right, where am I concave down? Concave down is anywhere in this graph that it cups. Oh, not cups. Concave down, concave up looks like a cup, concave down looks like a round, right? So it's kind of hard to tell, but does this piece here look like a cup or a frown? Kind of frown, so it's concave down. But where does it look like the inflection point is? At this -5, yeah. So I would suggest that, yep, that part's concave down. This all looks like a cup until you get to here where it looks like a frown. And this all looks like a cup, right? So where is this both decreasing and concave down? Well, it's where I have green, right? It's where they intersected. So it's from -7 to -5. And from 2 to 3. Is that cool? All right. It's a little bit easier doing it my way with the 2 different colors, right? I mean, you can really see it then. All right. Now let's answer it. Where is this graph increasing? Well, where is it increasing? Anywhere I go from a lower position to a higher position. Increasing, increasing. Concave down is the ones that we already identified, right? We already said this was concave down and this was concave down. Cool. Where do I got green? -1 to 2. Where do I have inflection points? Well, I have an inflection point where I do what, guys? Where I change from concave up to concave down, or vice versa, right? Where I have a change in concavity. So what am I going to do? Well, we already said that this was CC down and that was CC down, right? So that must mean CC up, CC up. So where did I have changes in concavity? Well, blue went to yellow, so at -5, and yellow went to blue, so at -1, and blue went to yellow, so at 3. So -5, -1, and 3. All right. Brandon, good? Right? Now here's the thing, guys. These are easy because I was actually looking at what? The graph, right? So this is f of x. If this is f of x, that's not too difficult to answer, is it? Okay, but what happens when it's not f of x? What happens when the graph above is what? The derivative, right? So can I see the graph that I'm going to start answering questions about? No, I can see the derivative now. Get the question changed, right? So let's go up here. Let's make no mistakes about it, right? Right now, this is the derivative. Let's just kind of like gather our thoughts, guys, because I'm already a little nervous. This is a different question. What's going on right now? Where is a graph increasing? Just answer the question. A graph is increasing when? Give it to me algebraically. What is greater than 0? F prime is greater than 0. When the derivative is greater than 0, I'm increasing, right? When do I have a local minimum? When I change from, to have a minimum, what has to happen? Minimum has to happen when I go from decreasing to increasing. When I change from this to this. Agreed? It's the only way I'm going to get to a minimum. When am I concave up? When second derivative is greater than 0. When do I have an inflection point? When I have a change in concavity. Does it matter which direction? No. Up to down, down to up makes no difference, right? That's a little bit, that's the difference between finding maxes and mins and finding inflection points, right? Inflection points, inflection point. Maxes and mins could be either, right? So you gotta really think about it. So anytime that happens, right? Okay, well, now we just hope to have the tools to answer that question, right? What tool do we have? We have a graph of the derivative. Well, where is the derivative greater than 0? The derivative is greater than 0 here, here, and here. Not here, right? Now Austin's looking at that like, dude, what? Hang on a minute. This is a graph of the derivative, right? The derivative being greater than 0 simply means that the derivative has to be positive. Read the directions. B, if the graph above is the graph of the function f prime of x. So we just changed the scenario, right? We changed the scenario. This is no longer the original graph. This is a totally different question. Got it? So where is this graph greater than 0? From -7 to -5. From -1 to 5, and from 5 to 7, yeah. And what did that little trick do? What did this little trick do? It excluded the 5 from the solution, right? Yeah, because 5 is not greater than 0, it's equal to 0, right? Cool? Where do I have a local minimum? Well, where did I change from what? Having a derivative less than 0 to greater than 0. Where did I change from being below to above the x-axis? Well, below to above, right here, correct? Anyplace else? No, just that -1. Now here's a problem, guys. I got a big problem. These two things require the what? Second derivative. I don't have the second derivative. I have the first derivative. You guys remember before break, we played the plus minus 0 game. And what does that mean? Slopes of the picture give me the derivative of the picture, right? So look at this picture. From here to here, what's my graph doing? What is all the tangents to this curve from here to here? They're all negative. What's the derivative here? 0. What's the derivative from here to here? All positive, because my graph is what? Increasing position, and then it's 0, and then it's negative, and it almost looks like it's it's so hard to tell, but it almost looks like it could be what? Almost vertical, but it's just so hard to tell. I'm not going to think that it is. And then it's 0, and then it's positive, right? So all I did, guys, right? All of these blue pluses and minuses, they all represent what? The second derivative. So where is the second derivative greater than 0? In other words, where is plus signs? From -3 to 2 and 5 to 7. Right? And then when do I have an inflection point? Anywhere I change from a minus to a plus or a plus to a minus, right? Well, minus to a plus to a minus to a plus. I got inflection points at -3, 2, and 5. Cool? All right. Again, the conversation totally changed, B, right? Because of what was told about the picture. All right. But again, if you know these facts, right, guys, the stuff in green is all the what? Justify stuff, right? Okay, that's all your justification. So even though it didn't ask for it, we're still going to write it down because it's easy. Helps me. If the graph above is the second derivative. Okay, so we got to get rid of all this. And it's now the second derivative. If the graph above is the second derivative, on what interval is, get rid of that word both. I don't know why it says both. In what interval, this word right here. On what interval is the graph concave down? Well, it's where the second derivative is less than 0, right? And what do I have a picture of? Second derivative. Where is the second derivative less than 0? Anywhere it is below the x-axis. So from -5 to -1. And at what x value do I have an inflection point? Well, I have inflection points when I have changes in concavity. Well, this is where it's concave down, right? What's this? Concave up. What's this? Concave up, concave up, concave up, concave up. Possible inflection point. But what is it after this? Concave up. So did I have a change in concavity at 5? No, the only place I had a change in concavity was at -5 and -1. Cool? Right? So again, this is a good little, it's kind of a good lesson to get us back into it because we're reviewing a lot of the rules that we did prior to break. Okay? All I want to do is this little piece here at the beginning of example 3, and then we'll be done, and you guys can do some work. Okay? It says the graph above is f of x. On the same set of axes, let's sketch and label a possible graph of the derivative and a possible graph of the second derivative. Sound okay? All right. Well, that kind of means play the plus minus game, right? And then take the plus minus game and draw it. Correct? So this is f of x. Let's play the plus minus game and then draw it. So what am I going to start off with here? From here to here, I'm going to do what? Minuses. And then 0, and then pluses. And then 0, and then minuses, and then 0, and then pluses. What do all of those represent? Those all represent slopes of the tangents to the curve, otherwise known as derivatives. So now all I need to do is take the pluses, minuses, and zeros and create a graph out of them. What's the ones I should probably do first? The zeros. Great idea. Gonna have a root here, gonna have a root here, gonna have a root here. Hey guys, quick question. Can a graph have derivatives at endpoints? No, so when I do this, guys, remember, at the ends of this, I have to have what? Open circles. Very good. Okay, here we go. So to get to this point, I have to be negative, right? Is that negative? Yes. And then to get from here to here, I need to be what? Positive. And then to get from here to here, I need to be what? Negative. And then after that, positive. That's a potential derivative graph, isn't it? All right, let's get rid of. Actually, we don't need to get rid of anything. That's good. All right, so now I want to take the second derivative, which means I need to play the plus minus game with the new one, right? How's that? Now what am I going to do? Take the pluses, take the minuses, take the zeros, and make a graph out of them. I need a 0. I need a 0. What do I need to be before this one? Positive. What do I need to be between these? Negative. What do I need to be after this? Positive. So doesn't it just look kind of something maybe like that? Cool? I'm going to stop there. All right. Guys, next time we'll look at an old AP question. We'll finish up. We'll do a couple more examples of things like these. But we'll ease our way in, guys. Cool? Does that sound good if we just ease our way in? Okay?